Hey guys, welcome back to Explore Electronics. In this video, let us continue our discussion with respect to vLSI. So let us see how the CMOS multiplexer will be designed, how the flip-flop circuit will be, and some memory design as well. And also alternative circuit representations other than CMOS. And let us see the differences between nMOS and CMOS circuit design technique. The very first thing is, we have already seen, if you want to have a implementation of these gates, means are the expressions like this. So if you have a whole bar, then only we can implement it using CMOS logic easily. And if you have A into B, we will be representing the AB gate inputs like this, and we need to connect it in series. Similarly, C into D we have, and we need to take C into D like this, and we need to connect it in series. Suppose if you get a plus functionality or functionality, then we need to do it these things parallelly. So this connection and this connection give us the parallel connection. And similarly, we need to have inputs in the pull-up as well. Pull-up in the sense the P network, but we need to connect it in a reverse order. Means if the series connections are there in between A and B, here AB becomes parallel. The two transistors with the gate inputs AB becomes parallel. Similarly, CD will be taken as this is C, this is D. So these two are series, here these two are in parallel. These two are in series, again these two are in parallel, and the complete thing will be exactly complementary to that, right? That is what the CMOS logic is. This is a block diagram structure. Here I have a gate level structure as well. This is A, this is B, and this is C, this is D, right? Similarly, this is A, this is B, this is C, and this is D. And also you can interchange this. AB can be written it over here, and CD can be right over here. There is no much difference in the output. So this is my output F. We need to take it from the drain ends of the transistors. This is drain. This is also drain and drain. This is our output. This we have seen already in the previous discussion, right? So let us take one more example. Like suppose if you have A plus B plus C into D whole bar like this. If this is the example we need to implement, then in a straightforward way, we can first take a N network and implement A plus B plus C. A plus B plus C in the sense 3 transistors should be in parallel with gate input A, gate input B, gate input C. Then into D means through this we need to have a D transistor in series. And if you implement this in a pull-up network, in P network, these 3 parallel things become series transistors with gate input ABC, and one transistor will be in series with this network, will be in parallel with this. This is the another example which is showing how actually the implementation will be. And also here you can write a transistor level circuit which I have not written. You can try it out simply replacing the blocks here with a P transistor representation like this. This is a P transistor, and whenever N transistor is there, you can also replace this by N transistor like this, right? Then let us see the pass transistor implementation and a transmission gate implementation. So pass transistor in the sense it is a single transistor which it will pass the value from one end to the other end, right? From source to drain we can say. And whatever the gate input we are going to give, that will be act as a control input. Means in the N transistor or nMOS FET, as we know, if the control input is 1, means if you are providing 1 from the gate, then only this transistor will be on, and it will pass the value whatever there in one side to the other side. So we say if this is input A and we are providing the control input as C, when it is 1, the output what we are going to get here is A and C. So if A is equal to 1, since the control input is 1, we will be getting the output as 1. If A is 0 and the control input is 1, we will be getting 0. So this gives us the AND gate functionality similarly. So we will be having A into C as output by taking this and this in a nMOS pass transistor. Okay. And similarly, if you have a parallel two such pass transistors connected, if one input is A, another input is B, and one control input is C, another control input is D. In this case, this A and C together we will be getting A into C over here, and B into D will be getting it over here. If we connect it parallelly like this, this will be giving us the plus functionality. Okay, this will add up, or it will be giving the OR logic. A dot C is like A and C, and B and D we will be getting. Then here we will be getting the OR operation between these two when we connect it in parallel, right? That we need to understand. If we connect it in series, we will be getting the AND operation. If we connect it in parallel, we will be getting the OR operation. And by utilizing that logic, the pass transistor can be replaced by a C switch, that will be a complementary switch, or we also call it as transmission gate TG. Okay. So with a transmission gate, we need to replace this, means the single pass transistor. We need to have one more P transistor as well. Okay. And the gate input will be reversed. This should be C bar. Then this will be connected together as A. This will be connected together as AC we will be getting, right? Now this becomes a transmission gate. If you have a single transistor like this, this will be a pass transistor. Since we have a disadvantage of passing full 1 in N transistor, passing full 0 in P transistor, we need to combine those two. This is the N transistor and this is the P transistor combined, and we will be calling it as a complementary switch. In this case, again, if we take a same example of this, we will be passing the value A, and we'll be giving the control input as C to the N transistor, and we'll be giving C bar as a control input to the P transistor. This is P transistor, pass transistor, and whatever we are going to get as output is A into C itself. A into whatever the gate input we are going for, N. But if you use both N transistor and P transistor over here, the full value of A, if it is 1 or 0, will be obtained as a output multiplied by this. Multiply in the sense AND operation, right? And now if you represent this with a block diagram, simply it is a C switch with input C, okay, and it will be AC. Now if we connect those two in parallel like this, so this kind of circuit, if we replicate it in a C switch, again we need to have two transistors parallelly connected for a single pass transistor replaced by transmission gate. Similarly, this single transistor will be replaced by a transmission gate with two transistors. If you have C over here, A over here, A into C will be obtained, but to the P transistor gate we need to provide C bar. Similarly, B into D will be the output over here. The P transistor gate input is D bar, and combiningly AC plus A into D will be the output. So by utilizing this logic, we can implement a 2:1 MUX easily using transmission gate as well as a pass transistor. You can see over here. So what is 2:1 MUX? 2:1 MUX will be having two inputs. This is first input, this is the second input. To select A as output, we should give select line as 0. If we pass B as output, we should provide select line as 1, like that. Means depending on the value of the select line, whether A is selected as output or B is selected as output will be decided. If you look at the truth table over here, if S is equal to 0, A will be our output, means A will be passed as output. If S is equal to 1, this S is equal to 1, B will be passed as output. That is the logic. If you write a expression for that, it is like A into S bar, means S bar is 0, plus B into S. So it is looking like the same expression what we have previously, right? In a parallel C switch connected. But the only thing is that we need to handle that whole bars carefully. So if you implement this, what is required? To get A dot S bar, we require one pass transistor. To get B dot S, we require one more pass transistor. To get this plus functionality, we need to connect those two in parallelly, right? Once we write the pass transistor circuit, we can easily replace that by transmission gate. If you see this circuit now, we need to pass A by taking S bar as the input from the N transistor gate. If you want A into S bar, A into S bar means this will be our input, and this S bar itself is my gate input. Then we'll be getting A into S bar. Then plus we'll be having B into S. This B will be my input and S will be my control input. So we'll be getting B into S. This is wrong here. This is B into S we will be getting. So combining these two together, connected in parallel, we'll be getting A into S bar plus B into S. Now this circuit will be act as a 2:1 MUX. The two inputs are AB and single control input is S, right? And remember this is B into S. Similarly, if you replace that by a transmission gate or a C switch, This is same. N transistor will be giving with S bar. That is also same here. And parallelly we will be having a P transistor, right? That should be with a complementary gate input. So it is S here. Similarly, this pass transistor also replaced by a transmission gate. This will be having B input, and N transistor will be getting S. N transistor will be getting S, and P transistor will be S bar. So B into S we will be getting. Again, connecting these two, we will be having A into S bar plus B into S. That is our output of a 2:1 MUX. This is the way we can implement any logic. It will be in a terms of AND OR using a transmission gate, RSC switch, or using pass transistor like this, right? This is also called as a CMOS logic, where we will be using a transmission gate functionality or a complementary switch functionality. So this is again the same indication. This structure we have seen so far already, and if you want to replace this by a symbol, these two by a symbol, it look like this. This is the symbol where this end will be a P transistor end gate, and this end will be a N transistor end. So here to the N transistor will be having S bar. So here is S bar. For the P transistor will be having S. So here is S. Similarly, in the second transmission gate, here we have S bar for the P transistor. So this is S bar. For N transistor will be having S. This is S. Correct? And since these two are S and S, we can connect it together and treat it as S. No problem. Here also we can connect these two together and treat it as S bar. No problem. Okay. These two are same, but we just representing with a symbol. And why it is S bar here? S here means here the below transistor is P and above transistor is S, but the symbol is tilted, and we are taking P transistor above and N transistor below. That is the only change. Otherwise, we can also write like this. Okay. Here we will be having a P transistor, so that you can connect S to this and S bar to this, and you can pass A, so that we will be getting A into S bar again, right? That you can try it out. Then we can have a kind of memory circuit using this C switch or a pass transistor. Okay. So the memory, in the sense, whatever the value we have, it should be stored internally as 0 or 1, and during the time duration we are going to store it, we need to refresh it again, so that it will be stored permanently. That is how the memories are going to work. There is two types of memories. One is static and another one is dynamic. Static, in the sense, we will be continuously getting the data from that. It will be permanently stored. Dynamic, in the sense, we need to refresh it regularly, right? So we can have such memory over here. You can see. So this is the memory structure. This is the memory structure. Here we will be having one inverter. Okay, one inverter. Another inverter is connected back, means it is connected like this. Suppose if you give value 1 here, to this inverter we will be getting 0. Again we will be having an input to the another inverter as 0, and we will be getting 1. So this 1 will be taken here and it will generate 0. This 0 will be taken here and it will generate 1 again. This process continues. So we will be storing 1 bit of data here continuously, right? So this is a one kind of such memory arrangement. If you want to write any value to this, how we can write? You can see here is the value D. This D value can be written. Whenever we want to write, we should have some control on the writing and reading, right? That's why we will be having load here. Whenever load is equal to 1, whenever this load is equal to 1, you can see the second diagram with this load is equal to 1. Here we will be having a N pass transistor. Here we will be having a P pass transistor. Okay, or a transmission gate with N input as here LD, and here the P input is LD, like that. Okay, you can assume it as a pass transistor directly. When LD is equal to 1, load is equal to 1, we will be loading the data into the memory. We will be loading the data into the memory, right? This is the data and this is the memory. We are loading it. So if you want to pass this value D as 1 to the memory, we need to make this transistor on. We need to make this pass transistor on. Here we will be having a pass transistor like this with load. When this load is equal to 1, this will be a continuous, it will be short, and whatever D we have will be passed. That is what happening here. You can see this switch is on now when we giving load is equal to 1. This will go to this inverter, and whatever the value we have given, inverted version of that will be available in Q bar, and the as it is version will be available in Q. At that stage, whatever the value we have written will be, we can read it out, and this switch will be off at that time. If you want to store it in a longer duration, after the load is done, we need to make this load is equal to 0. Means we are not at all loading. At the time of not loading, we need to take it out. Means it is off now when load is equal to 0. This will be on. At this time, this memory will be keep on getting the same data. Suppose if we load the value 1 will be there here. It will give 0. It will take the same value and it will invert it again. This 1 0 1 0 is happening continuously, right? So Q bar will be getting 0 and Q will be getting 1 continuously. This process is never ending. Since we have inverters connected back to back, these things will be inverting the things continuously. So this is a loop, it will be storing the data permanently. To have a control on writing into the memory and store it there, we will be having a load signal here that will be controlled by 2 pass transistors, right? This is a kind of memory implementation. Then comes the different ways of writing the circuit. One such arrangement is CMOS logic. This we have already seen. Let us quickly look at it. In the CMOS logic, we will be having a P transistor network here, and below we will be having a N transistor network. And the output will be generated as 1 from the VDD through a P transistor network. That's why we call this as pull-up network. Means this will pull the output to 1, right? Who is responsible for generating 1 in the output? P transistor. That's why it is pulling the output to 1. We call it as pull-up network. This nMOS transistor network is responsible for connecting the output to ground. That's why this will be called as pull-down network. It will pull down the output to 0. The meaning why it is called as pull-up means this network is responsible for pulling up the output to 1, and this network is responsible for bringing that to 0. That's why it is pull down or pull up. In CMOS arrangement, pull up network is P and pull down network is N. And we know that if you want to implement A plus B whole bar, the pull down network should be in parallel with gate inputs and pull up network should be in series. Similarly, if you want to implement A into B whole bar like that, pull down network will be in series, pull up will be in parallel. These things we have already seen. To implement the same structures in nMOS logic, how actually it will be? Now this is the nMOS logic we need to understand. In nMOS logic basic structure, if you see, the pull down network what we have in the CMOS network will be same. The same nMOS network will be act as a pull down network. This is responsible for bringing the output to 0. But who will bring the output to 1 means the pull up network, and it will be a single depletion type N transistor is a pull up network. And the arrangement is that gate will be always connected to drain and it is connected to output. That is the arrangement. So what happens if we connect like this in a depletion type transistor means always this depletion type transistor will be on and depending on this output D. If output D is above its threshold level, this transistor will be always conducting. That is how the arrangement is. So it will be easy to pull up the output since this transistor is always on. So if you want to bring the output to down, we need to enable these transistors, right? Means if you see this structure, Y is equal to A into B whole bar. The similar series arrangement of transistor gate input A, B is connected here in pull down. Pull down will be same as CMOS network. Pull up will be again single transistor with gate input connected to drain. Here what happens when A into B whole bar functionality, if you want to bring it to 0 means we need to provide A is equal to 1 and B is equal to 1. Then only the output will be 0. If any one of the input, if this is 1 and this is 0 means what? This transistors will be on and this will be off, right? This is off. So anyhow we will be not getting that to ground. So for 1 0 obviously the output is 1 through this, right? Similarly for 0 1. Similarly for 0 0. Only for 1 1 this line will be anyhow connected to ground. We can pull down even if it is connected over here, right? So when these two are on, we can bring it to 0. When these two are off, we can bring it to 1. Similarly, if you look at A plus B whole bar representation, these two transistors will be connected with gate inputs AB, and again a single transistor will be act as pull-up. So here the difference between the CMOS and nMOS network is that this CMOS logic requires how many transistors to construct? If we have A plus B whole bar as a expression, there are two inputs A and B. We require two transistors here and two transistors here. Means we require 2 into number of inputs. 2n transistors are required for n inputs. If you look at the nMOS logic, the advantage is that here for the n inputs, for the 2 inputs, we require 2 pull down transistors and 1 pull up transistor. So n plus 1 transistors are sufficient to implement. So this saves the area. The area requirement can be reduced using nMOS logic. But the only thing is, since this transistor is always on, there is a leakage current flowing through and it will disturb the logic always. And whenever these two transistors are 1, directly these transistors are also connected, this also connected, this also connected, and direct connection established from VDD to ground. We call it as line to line short. Okay, there is a huge current flow from VDD to ground happens when all the transistors of the pull down network is on. That is the disadvantage, right? So we need to understand the differences between nMOS and CMOS logic now. So if you look at the logic levels, how it is going to display or how it is going to bring up the logics. I said in CMOS logic, pull up is responsible for bringing the output to 1 and pull down is responsible for bringing the output to 0. So it is fully restored logic. We can easily connect to VDD and we can settle the output to 0 as well. But here in the nMOS logic, output does not settle to ground easily. Why? Because we will be having a pull-up connection always on. So it will not settle at ground. Means if you have a logic levels like 1 and 0 as 5 volt and 0 volt, this 0 will not always be 0 in nMOS logic. It will remain in 1 volt or like that. Because of the pull-up transistor always trying to bring this voltage to the upper level, right? That's why we will be having an issue with the noise margin when we are using nMOS logic. Similarly, if you look at the transmission time, rise time and the fall time. Rise time in the sense from 0 to 1, how much time it takes to rise its value. From 0 volt to 5 volt, how much time required to do that is rise time. Similarly, from 5 to 0, how much time to decrease its value to 0 is fall time. So both are same here in CMOS logic. Here rise time will be inherently slower than fall times. And transmission gates, if you take, transmission gate passes both the logics well here. Output of the transmission gate can drive the another transmission gate easily. But in the nMOS logic, there is no concept of PMOS at all, right? There is no usage of PMOS logic in the PMOS transistor in the nMOS logic. So pass transistor we are going to use only the N transistor. So it will pass 0 well, but it will degrades 1, right? That is what the nMOS disadvantage is. If you come to the power dissipation, this will be having 0 static power dissipation. Why? Because sometimes pull up will be on, sometimes pull down will be on. At a time, both the logics will not be on in CMOS logic. But in nMOS logic, pull up will be always on. So there will be a power dissipation more with respect to static power consumption is concerned. And there are some pre-charge characteristics as well. Both N-type and P-type devices enable the efficient pre-charge buses to VDD and VSS in a short time here, pre-charge characteristic. And enhancement mode transistor require bootstrapping or hard clocking to pre-charge it to VDD. And that is what the pre-charge characteristic is. Some differences you can easily make out here. These are the easy makeouts. This needs some understanding of how actually the transistor works. And a power supply, if you take, voltage required to switch a gate is fixed percentage of VDD. Here somewhat dependent on the voltage value what we are going to give. And voltage range can be from 1.5 to 15 volts here. It will be a fixed supply voltage here. And this you can easily remember, it requires 2n number of devices to construct a logic or a circuit. This requires only n plus 1 devices to construct a circuit. And this also requires some understanding of the working of the transistor. and how actually we need to keep the ratio of the pull up and pull down transistors is 1:1 or 2:1 here. Here it is more. It means pull up transistor should be more stronger compared to the pull down transistor here to maintain the ratio. That is 4:1, right? 4 times bigger transistor will be using in pull up single depletion type transistor. Pull down transistors will be having 1:1 ratio like that. And layout, if you see, CMOS encourages regular layout styles. But here in the nMOS, because of the depletion load or the depletion pull-up transistor, different driver transistor sizes need to be added, right? So another thing which I have not explained you clearly here is what is enhancement type transistor and what is depletion type transistor. Enhancement type transistor, in the sense, if you see the physical structure of that, it will be having a source and drain and also gate over here. Whenever we apply the voltage from gate, this channel between source and drain will be created in an enhancement transistor. But in the depletion transistor, at the time of manufacturing only, we have a channel between source and drain, and if you give the positive voltage from gate, it will increase the current flow. But to seize this channel, seize means to remove this channel, we need to give the negative voltage from the gate. Here the channel is already created. Here the channel we need to create by applying the voltage from gate. That's why, because of the channel already created at 0 gate voltage itself, this transistor will be always on, we say, right? And also you can see there is a thick representation in the channel region. This says channel is already present at the time of manufacturing itself, right? That is a depletion type transistor. Enhancement type, in the sense, there is no channel exist until we give some positive voltage from the gate. The channel will not be existed. If we apply the voltage from gate, then only the channel is created between source and drain, right? That is the difference between enhancement type and depletion type. In later videos, let us see more about how the working of enhancement type is and how the working of depletion type is, so that you can understand more about the working of these nMOS and CMOS logic clearly. And please subscribe to both the channels. This gives us the information about the syllabus and the content present in the VTU. And this second channel give you the more idea about how the industry works on vLSI. Thank you.